Section 8.2, graphing f of x equals ax squared plus c. We are going to expand on our parabolas as being more complicated in their equations. Rather than just f of x equals ax squared, we're now going to add a constant c onto the end. Now the value of c affects the vertical position of the parabola, and it's easiest to identify looking at the vertex. For all the parabolas that we've looked at so far, the vertex has pretty much been 0, 0, right here at the origin, and that's for anything that's ax squared, whether it opens up or down. But if I attach something to the end, a plus c, and that c is positive, greater than 0, it's going to shift the vertex up. So this blue parabola has the equation y equals x squared plus 3. The vertex, you'll notice, is at the point 0, 3, which is shifted up 3 units from the origin. The red parabola has the equation y equals x squared minus 3. That c that I'm attaching to the end is negative. It's less than 0. That leads to a shift down. You'll notice that that has been shifted 1, 2, 3 units below the original vertex. As a matter of fact, all points are 1, 2, 3 units below where they originally would have been on the parabola y equals x squared. You can see 1, 2, 3. So it's easiest to do from the vertex, but it's true actually of all points. It doesn't have to be 3. It just so happens that in both of these examples, I've used 3 to demonstrate it. But in general, attaching a positive number to the end shifts the parabola up. Attaching a negative number shifts it down. All right, we're going to try to graph g of x equals 2x squared minus 3. One way we can do that is by using a table. Now, what I've provided in dotted lines there is a sketch of y equals x squared, so we can have that as a comparison. We want to just start by picking values for x, and it's always easy to start with 0, and then we can add in maybe 1 and 2 to the right, and negative 1, negative 2 on the left. Now when we plug in, it's important to follow the order of operations. I'm going to do 0 for my x and then square that. That gives me 0 times 2 is also 0, and then I'm going to subtract 3. That gives me the point negative 3. When I plug in 1, I have to make sure that I square the 1 before multiplying by 2. So I'm looking at 1 squared, which is 1, times 2 is 2, minus 3 is negative 1. Now I do the 2 squared. I take the 2, plug that in for my x, and I get 2 squared is 4, times 2 is 8, minus 3 is 5. Now at this point, what I might remember is that the axis of symmetry is going to be the line x equals 0, because that's going to go right through my vertex. It's going to be that vertical line. And so I'm going to be symmetric on the other side of that. So when I plug in negative 1, I should get the same thing that I'd get from plugging in 1. That would also be negative 1. And when I plug in negative 2, I should get 5. We can check that just by plugging in, but remember that squaring a negative gives you a positive answer. Now these 5 pairs of numbers correspond to ordered pairs, so I'm going to plot those points on my coordinate grid. So you'll notice that I actually had to shift up my coordinate grid in order to fit my vertex on there at 0, negative 3. And now I'm just going to connect these with a smooth curve, or at least as good as I can do. And I don't want to have it be too pointy. I missed it a little bit there. You get the general idea. It would be a little bit better if I kind of connected right through. There we go. That looks a little bit better. And we can show that it continues up either way. And now just to compare this to my original parabola, it does open up because my a is positive. It's actually a little bit narrower than the original parabola, and that's because my a is a number bigger than 1. The absolute value is bigger than 1. And you can see that my vertex and all points have actually been shifted down below where 2x squared would be. But specifically, my vertex is easiest to see. I've gone down 3 because I've subtracted 3 from each side. And that's all that you have to do in order to graph. All right, let's take a look at just another example. If I have f of x equals negative 1/3 x squared plus 2, I have a coordinate grid here that features a sketch of y equals x squared. So we have something to compare this to. And I just want to start by picking some values for x. Now, because I have a fraction, I want to be careful about how I choose these. I always want to pick 0, and I want to make sure that I can kind of get rid of this fraction. So I'm actually going to try to choose 3 and -3, because my denominator is 3, my fraction. Now, this is going to be a little problematic, because if I get too big, if I pick the next multiple of 3, which is 6, I'm going to end up with a really big number. So we're just going to see exactly what it looks like to use a decimal, and it'll be okay. I'll use 4 and -4. Now when I go to plug in these numbers, 0, I know where that's going to take me to. It's going to take me immediately to 2, because 0 squared is 0, then multiplied by -1/3, still sticks at 0, so then I can add 2. When I put in the 3 for the x, that's going to give me 3 squared, which is 9, and then -1/3 of that is -3. Add that to 2, and I'm looking at -1. Because of the axis of symmetry, I know that -3 is going to work exactly the same way. 4 gets a little bit trickier, and I'm going to write that one out here. If I look at f of 4, I'm looking at -1/3 4 squared plus 2. Now, that's -1/3 of 16 plus 2. And if I do that out, yeah, I could look at it as -16 over 3 plus 2, but that's not particularly helpful. I'm probably better off expressing that as a mixed number, which would be -5 1/3 plus 2, which is -3 1/3. That's going to allow me to put my answer on the graph where I need it to be. So I'm going to put this in as a fraction, -3 1/3, and that's going to be the same thing for -4, -3 1/3. So now I can plot these points on my coordinate grid. Now what you might notice here is that for the point -4, -3 1/3, I went down to -3 and just a little bit further beyond that. Now that I have my 5 points graphed, I connect them with a smooth, as smooth as I can do, curve to show that the parabola extends. And you can see what I have here is a parabola that opens down, which is something I expected since my value of a was negative. It also is wide compared to the original parabola, and that's because the coefficient a is a fraction that's less than 1, or at least its absolute value is. And it also is shifted up 2 units from the original vertex, and that's because of the +2 that's attached to the end. All right, I hope this is clear. Now I want you to give it a try. I've provided, once again, a graph of y equals x squared, so you have it for comparison. And I want you to graph h of x equals 0.5 x squared plus 2. Don't be afraid to have decimals or to pick points that are going to work conveniently for you. And there you go. Pause the video, try to plot it using at least 5 points, and then compare your answer to what you see. All right, here's how your graph should look. And there you have it. Probably the points that you would have been most likely to use would be 0, 2, maybe 2 and -2, 4, and perhaps 4 and -4, 10. Those are probably the easiest ones, but any other points would have been somewhere along this blue curve. You'll notice it shifted up 2 units from the original vertex of 0, 0. It opens up because my coefficient is positive, and it's wide because my coefficient is the fraction that's less than 1. All right, now you know how to graph any parabola that looks like ax squared plus c. A 0 of a function f of x is an x value for which f of x equals 0. So sometimes a 0 is the number 0, but otherwise it's any number that you would plug in to make f of x equal 0, to result in an answer of 0 once you plug in. Graphically, these correspond to the x-intercepts of a function. You can look at my first example here. I have an x-intercept right at 2. This parabola comes down, hits the x-axis, and turns right around. This function has one x-intercept, it means it has 1, 0. 2 is a 0 of that function. If I plug in 2 in here for x, and I get y equals 2 squared minus 4 times 2 plus 4, y will equal 0. In another parabola, you'll notice that my parabola goes down below the x-axis and then comes back up. So there are two locations at which this function has an x-intercept, somewhere between -2 and -3, closer to -3, and somewhere between 0 and 1, somewhere closer to 1, maybe around 0.7 and -2.7 or something like that. Those are the two zeros of the function. Those are the two numbers for x that you can plug in to this equation in order to get 0 for y. We have one other example. This is a parabola that starts above the x-axis, turns around before it reaches there, and continues going up. Because of the nature of the parabola, it's never going to hit the x-axis. So it has no x-intercepts, therefore it has no zeros. This function, y equals x squared minus 2x plus 4, there's nothing you can plug in for x and still get 0. So we have three different types of parabolas here. The first one, in which we have 1, 0, which is at 2. The second example, where we have two zeros, somewhere around 0.7 and -2.7. And we have our third example, where we have no zeros. There's no number we can plug in there to make that y value equal 0. This is going to be very helpful in terms of using these types of properties of parabolas in order to solve problems. Alright, so now let's see how we can use the zero of a function to solve a real-world problem. We have here as an example where we have a person dropping an object from the top of a 64-foot building, and we can use a function f of t equals -16t squared plus 64, and that's going to model the height, which is f of t, feet, of an object that's dropped after t seconds. The first question is, how many seconds pass before the object lands on the ground? So what we're looking to find here is when the height of the object is it's at ground level, that would mean the height would be 0. So we're really looking to make this function equal 0. What we're looking to do here is find the zero of a function. And so one thing we can do with that is we can put 0 in for f of t. We have 0 instead of f of t equals -16 t squared plus 64. And that's something we might actually be able to factor if I rewrite it as 64 minus 16t squared. I might notice that it's a difference of squares. And so in order to factor that, all I'm going to do is realize that this is going to be 8 plus 4t times 8 minus 4t. Now, from that information there, certainly I could have taken out a GCF first, but I actually have the ability to deal with that after because it's a special product. Since this still equals 0, I'm going to get two different answers when I split and solve. Pretty easy to see that from the first set I'd get t equals -2, and from the second one, I'd get t equals 2. Now, since we're talking about the time that it takes for something to fall, we're certainly not going to count a negative time. So I'm going to disregard that first option, and we're going to stick with the second one, t equals 2. So we want to make sure we put a proper label on this. So how many seconds pass before the object lands on the ground? We say t equals 2 seconds. Alright, so then we can actually look at another question here, which is how would a different height of the building affect the answer to A? So let's say the building was actually above 64 feet. What that means is that it's going to have a different form of the equation, right? Our function would be f of t equals -16t squared. Now we're shifting it up, so we're going to be increasing it by a larger number. So maybe we say plus 80 feet. Well, if that's the case, we need to still figure out when this is going to hit the ground, when it's going to be 0. And so maybe we don't know exactly what the case is, but we can just compare it to what happened when it was 2 seconds before. And so if I look at f of 2, it's going to be negative 16 times 2 squared plus 80. 2 squared is 4 times negative 16 is negative 64 plus 80. So that's going to give me 16. This means that after 2 seconds, which is the time that I put in, the amount of time that it would have taken to fall to the ground before, I'm still 16 feet off the ground. Well, I have further to fall. That means it's going to take longer to fall the rest of that distance. So even though we haven't figured out the exact time that it will take to fall, a taller building means that the amount of time required will be larger. Similarly, a shorter building will make the ball hit the ground or the object hit the ground in less than 2 seconds. And that's just a simple application of using a zero to figure out some information about a real-world scenario.